Okay, hello everybody. Welcome to Operations Research video lecture. We are on chapter 6 on the lecture notes, linear programming with SPICE. We have introduced a diet problem and compared it to the product mix problem of chapter 5. I hope that you have just watched again the video on how to solve the product mix problem, so the videos related to the chapter 5. Now we are doing pretty much the same thing for this diet problem 6.1. So we have the problem data here, and we want to buy these cakes with as cheaply as possible, so at the minimum cost. And what are our constraints? The constraints are that we have to have this amount of nutrients for the population of the seeds, tabro. Yes. And now you can follow the algorithm 5.2, I think it was. Let's not guess. It's here 5.2, as was done in the case of a product mix problem. So we have to find the decision variables, then we find the objective function, and then we find the constraints. And what are those in our cases? Well, the decision variables one. So what Naib-Stilgar has to do? Well, he has to feed the seeds. Feed with what? Well, with Fremen cakes. So Naib-Stilgar is going to a more deep bakery and ask, buy so and so many Atreides cakes, let's call that x1 again. So and so many Corrino cakes, let's call that x2. And so many Harkonnen cakes, let's call that x3. And the price per cakes they are given here. So the objective function is, it's actually the same objective function as in the more deep bakery problem, except, so it's here. Let me put this slightly even bigger so you can see. So if you look at this cost, it's the same. So we are buying x1, x2 and x3 numbers of Atreides, Corrino and Harkonnen cakes, and these are prices per cake. So obviously the price is the same. But now, well, here is the, in some sense, duality or balanced point of view that, obviously more deeps want to maximize because they are selling, and we as Naib-Stilgar, we want to minimize because we are buying. So this is not a maximization problem but a minimization problem. And then I use here the simple W. Again, I could have just used a variable name cost for more descriptive. I use W, and why W and not Z? Of course I could have used Z. There's nothing deep here. The reason is that why I use W is, first I want to make a difference. So I have used different notation. So because I'm going to compare this with the more deep bakery problem 5.1, and the Z is used there. So I have to use another symbol, and also it's relatively typical that if you have a maximization you use Z, and if you have a minimization you use W. This is, there is no fixed standard, but this is a rather common way of doing it. So we know the objective function. Okay, so now we are, step 1 was the decision variables. This is done. They are the same as in problem 5.1 for the more deep bakery. Problem 2 is the objective function. Well, that's the total cost, and as a function it is the same as in more deep bakery, but now it's the objective is to minimize and not to maximize. So then the step 3, which is typically the hard step or the step you have to work the most, and this is the constraints. And somehow they are very, very similar to the more deep bakery. So what was the more deep bakery constraint? So they were, this was the availability of the stuff they had, the nutrients, and this is how much was needed for each cake. So it was all these lines were upper bounds, so less than equal to. So it's almost the same for us. So for us, these bounds here, the number of nutrients, they are not the available nutrients, but it's just the opposite, the nutrients we need. So for example, let's take this water. So the seeds requires 300 liters of water. So for each Atreides cake, we get 600 milliliters, each Corino 800 milliliters, and each Harkonnen cake 500 milliliters. So then, putting this either this in liters or this in milliliters, so let's represent all these water constraints. Let's use unit milliliter. So we get a water constraint like this. So 600 times x1 plus 800 x2 plus 500 x3. So what is the number here? Sorry about this paint's kind of funny way. So this. So if we buy x1 x1 Atreides cakes, x2 Corino cakes, and x3 Harkonnen cakes, then this is the amount of water we have. So the water is distributed in these cakes, but that's the water we have. And we need in total 300,000 milliliters of water. So this must be at least this. And same for all the other fat, sugar, protein, water, and spice. And again, the sign constraints are there, just to make sure. And again, I should say that if I sometimes forget to say that the sign constraints, I probably made a mistake, because they are so prevalent. They are typically there. So if a sign constraint is missing, I mean, some of the variables are allowed to be negative. That's something that I usually tell explicitly, because that's not the normal situation. Okay, so here we really have this LP model 6.2 for the problem 6.1. And here is, you can in the notes click there in page 5. I will not do it now. Well, why not? Here we have, again, if you recall, that was the more deep bakery LP. And if you compare this LP model to this LP model here, you see that they are almost the same. Difference is that the maximization goes to minimization, and these what were lower bounds there are upper bounds here. So this is an extremely closely related to the more deep problem, so its solution must also be extremely closely related. And yes, indeed it is. And here is the solution for it, 6.3. And again, you can and you should download this M file to yourself. So you just click here. And for example, for me, it's some opens web browser, in my case Firefox, then asks what to do with this, so you save it, and then, well, now it's saved. It goes to my somewhere, and then, yeah, well, for me it goes this down. Here you see it's Tupper diet, and then I have to move this to my working directory, I mean the directory I use with Octave, so it's a spicy OR here. For example, since I have a shortcut there, I could just drag and drop there. And since I have it there already, now I have to figure out whether I replace it or actually don't do anything. Well, yeah, okay, let me replace it. It's the same file. Okay, so let's analyze this file now, and we can do it actually very quickly. We can analyze it here on the notes, but let me, again, since it's a M file, let me open Octave. So here I have Octave open. Let me make this window so that it's not behind my face. So like this. And let me move this like this. And again, the first thing when you start Octave, check that you are working with the correct directory. This is not for me that, so I have to change it. So I could change it here, or I can issue command cd like change directory, and then I will do it like this because it's faster, because I can use tabulator to autofill the directory. Now I have a correct directory, and let's hope I probably have here M file diet. I should have it here somewhere. Oh, it was called Tabor diet. Yes, this. So I should open it in an editor to see what's going on. Let's try double click here. Does it work? Oh, it does. So it opens the editor tab and this one here. And what I actually now, how I will show this to you, I will not go through this file in detail. Instead, I will actually kind of show how I did it. And this is kind of maxim in at least with programming or working with computers, and I think this is how the universe works. So copy paste, that's your friend. So let us look at the modedeep.m here. So what I actually did in writing this Tabor's diet problem, let's see what we have here. We have a modedeep bakery problem 4.5 from Octave with Spice. Sorry. Okay, this is of course also a solution. Let me, yes. I actually used this. I didn't use the modedeep revisited, but doesn't matter. This also solves the same problem. So this is from the Octave with Spice notes. Of course, this problem 4.1 is the same as problem 5.1, and this is a solution. So in Tabor diet, let's see. Okay, I just, of course, change the title. Then there is a data. So what is the data in this? Well, we have, as always, we have somehow C, A, and B. We have the objective function defined by the vector C. A is a technology matrix that tells how nutrients are turned into cakes, or what are the contents of the cake. How do we get nutrients out of the cakes? I mean, how they are related. And then there we had a requirement for the nutrients, and this was in the modedeeps. It was availability. But if you look at what is here, so this is the seeds Tabor, what we are solving now, and this is the modedeep, what we solved previously. And these are, I mean, they are I have a little bit of different spacing, so you can see how it changes, but that's just style. There's nothing different here. Comments are slightly different because, yeah, we are doing a different problem, but C, A, and B, they are the same. I mean, of course. That was just copy paste. So what's here? So this was the modedeep. Xmax, Jetmax, GLPK, CAB, lower bounds, upper bounds, they are not there. Constraints are upper bounds. three variables, they are continuous, and this is maximization. Now look at this line. Line 28. Okay. There is something different, but not much. So what's the difference? Okay, I call the solution X and W. That's just, I decided I could call them anything, of course. So here I called them X max and Z max. So the difference is that I called them, well, certainly not X max because the minimization, I could have called it X min and Z min. Yeah, why not? That would have been more logical, I suppose. But I just call them X for short and W for the minimization for short. So what comes next? So this is something that you probably have seen before, and you will see this a lot. So GLP, KCAB, empty matrix, empty matrix. This is quite typically how we start things. And then comes the difference. So in this more deep, we had upper bounds. So there are 1, 2, 3, 4, 5 constraints. They are all upper bounds. Well, in Tabor diet, they are lower bounds. We have 1, 2, 3, 4, 5. Basically, they are the same. So everything is same except that instead of upper bounds, we have lower bounds. So this is L for lower bounds, and this is important, it's not a maximization, it's a minimization, which means that this is not -1 but +1. And we could have also simply omitted this because the default is the minimization. So if it were like this, that would be the same. Now then it's a matter of taste whether we put it there explicitly or not. All right. So let's see what happens. So it was Tabor diet. Okay. So what I did, I just typed Tabor, and let's hope that there is nothing else starting with Tabor. So Octave will understand if I press tabulator what it means. Yes, it does. I hit enter, and there I get it. So this is the solution. All right. So now let's get back to the notes and see first that this is the same solution as here. So here I have in this file commented basically this what I just ran. And yes, it is the same solution. And here for comparison, I've also run the more deep and look at the solution there. We'll come back to that later, very soon. All right, here on page 11, there is pretty much the same thing that I explained just a while ago. All right, now we have the solution. And let's not analyze it further except that we see that they are not the same. More deep and Tabor diet, they had different solutions. And what happened there? So the first thing to understand what's different is that now you might think that since the problem in somehow in the table is the same, that we are buying all the nutrients that are turned into cakes, and then with the cakes we get the nutrients. So that would be the balanced case. But that's not actually the case. We are buying the cakes, and in doing so, it actually happens that if you look how much nutrients are required for those cakes that we are buying daily, it turns out that it is more than the nutrients that the more deep bakery has daily. So there is an imbalance here. So let's hope that the more deep bakery has some reserves, some warehouse, we can buy yesterday cakes. Otherwise, this is, if we want to have a day by day balance, this is not going to work. So this is exercise 6.4. More deep needs more nutrients. So if you look at what more deep bakery problem 5.1 does, it turns the nutrients into cakes, and then if we want to go there and buy cakes, and there are only those amounts of cakes that the more deep bakery is doing every day to maximize its profit, there are not enough cakes. You can see it here. More deep daily makes 171 Atreides, 246 Corrino, and no Harkonnen cakes at all. What we want to buy is 415 Atreides cakes, 61, so there are not so many daily. Let's hope that there are reserves. Yesterday cakes. We want to buy 61 Corrino cakes. Okay, there are plenty of them. We are not buying them, all of them. And then there are 452 Harkonnen cakes that we want to buy. And yeah, okay, this is somehow we are not getting along very well, because the more deep bakery tells us that they don't want to make any Harkonnen cakes at all. So the moral of the story is that even though if you look at this table, it is the same problem, but we look at just the opposite sides. So we either sell or buy, and the available nutrients and the required nutrients are the same. But the solutions are radically different. I mean, as a solution, as the way to program, I mean, to calculate the solution, tell the solution to Octave, they are almost the same. So there is no difference here. But in the solution, there is huge difference. And yeah, this 6.4 exercise is the kind of first thing where we see the difference. The difference is that, yeah, the more deep bakery is not going to, doesn't have enough nutrients. And maybe I should say that this is the kind of a dishonest question. So how much nutrients should more deep bakery have in order to be able to meet seed starter diets? The answer is not to calculate things. Okay, this is a bit of a nasty exercise, but it is on purpose nasty, because this is the first question that you have comes in mind, and then you maybe think that there is a solution to it. Okay, I give you a hint. I don't think there is a solution to this. At least not an obvious one. Then the next one, 6.5, and this is the kind of a bit theoretical, or something that you have to consider, not calculate, but really to contemplate what's going on here. So is there something? So we had just an example. So let's take away. Let's forget planet Arrakis, and let's forget Muad'Dib. Let's forget Fremen's. Let's look this simply from the abstract, theoretical or mathematical point of view. So what did we have? So we have a LP data with C, A, and B, and this time it's good to know that all these were positive numbers. So all the costs were positive, all the mixing were positive, and all the requirements or availability were positive. This is sometimes something that you forget, because it's typically so very natural, but maybe sometimes they could be negatives. So now understand that they are positive. And what did we do? We considered two LPs. So this 6.6, this was the selling part, or the seller's side. So this was the Muad'Dib bakery. You want to maximize C transpose x. And the constraints were as usually in the maximization, they are upper bounds. I mean, if everything is positive and it's lower bound, I mean, it's very easy to maximize. Then you just let x go to infinity. So of course in maximization it's natural to have upper bound, so it's ax less than equal to b. And the sign constraints almost always there. So then the other way around. So this was the bias side. So this was the Naive-Stilgar. So Naive-Stilgar wants to minimize, and let's call it W now. So it's not clashing there. Yeah, and obviously it's the same cost function, C transpose times x. And what about the constraints? So yeah, same kind of thing. It's the same technology that combines nutrients with the cakes. They are the same. And then ax bigger than equal to b. Okay, these b's are the same, and this is obviously the other way around. And as I said, for maximization, it's typical that there's upper bounds, because otherwise it's easy to maximize. You just let x go to infinity. Well, here, if you look at the minimization other way around and remember these sign constraints, then if this were the other way around, it would be easy to minimize this. You just put x go to 0. So now it's the other way around. Okay. And then it actually happens. So this is a general, well, you could call this theorem. This is a buy-sell comparison theorem. So if z star here is the solution of this, I'm not looking at the optimal solution x star at all. This is only on the level of the cost, not the optimal decision. So if z star is the solution here of this maximization, and w star is the solution of here of the minimization, it's always so that z star is less than equal to w star. This happens always. So the seller's optimal solution is not as much as the buyer's optimal solution. You can see as an example here. So the seller is 6 point something to the 10 to the power 4, and here we have 1 something 10 to the power 5. So obviously this w here is bigger than the z max here. All right. So you have to argue, or if you want to be a mathematician, prove, it's the same thing basically, that this happens always. Okay, and then there is an additional question. So we always had C, A and B positive. So is this necessary here? Could it be that this is a very, very general theorem, that whenever you have a maximization and minimization related like this, then the min solution is always bigger than the max solution, even if C, A and B, some may have negative elements. So is it true also in that case? That's yeah, either it's true. If it's true, you have to prove it generally, or it's untrue. And how to show that it's not true? Well, you can, for that to show that something is not true in general, it's enough to find out one counterexample. So now first you have to guess if it's true in general. Try to argue so that it's true in general. If you manage, good. If it turns out to be very difficult and you don't manage, then maybe it's not true. Then you should try out to find, maybe you can find a counterexample. All right. That was the story about the diet problem and its comparison to the product mix problem. This exercise 6.5, I think this is a very, very good thing to remember. And also to remember that this, okay, they can be the same, but usually they are not the same. In our case, they were not the same. So this was not the problems were not in balance. So now you could think, is there a way for knife Stilgar to look it in a balanced way so that More Deep Bakery and knife Stilgar can make an agreement and both are happy? This approach that knife Stilgar now did, trying to buy the cake so that the nutritional requirements are met, is not going to. The negotiations will be hard because the situation is not in balance. But this is the topic of the next section. See you.